Hi everyone! Today I want to introduce something called Big O analysis. Big O analysis is something that comes up often in software engineering interviews, and it's a good thing to know on the job as well. So let's go ahead and get started. What is Big O analysis? Big O analysis is analyzing the efficiency of an algorithm in terms of the input size n. Big O analysis can be used to analyze the time complexity or the space complexity of a piece of code. Additionally, Big O analysis is always concerned with the worst case scenario, rather than the best case or the average case. So, why is Big O analysis useful? Well, absolute runtimes of an algorithm vary based on the machine the algorithm is run on, whereas Big O analysis is machine independent. Also, Big O analysis allows us to analyze the efficiency of a piece of code just by looking at it. Overall, Big O analysis is useful because it provides us with a standardized way to discuss the time and space efficiency with others in a meaningful way. Now that we know what Big O analysis is, let's go over some general rules. The first rule is there are no constant factors in Big O analysis. For example, if we had an algorithm with a runtime of Big O of 2n, we would reduce that to Big O of n. The second rule is we drop lower order terms. For example, if we had an algorithm with a runtime of O of n plus O of 1, we drop the O of 1 and say the runtime is O of n, because O of n dominates the expression. Here's a chart of the most common runtimes, ordered from fastest to slowest, with the fastest runtime at the top and the slowest runtime at the bottom. Let's go over this chart together. O of 1 is called constant time, since the runtime does not depend on the variable input size n. O of log n is called logarithmic time, and that's when we have an iterative or recursive problem where in each iteration or recursive call, we reduce the input size n by some constant factor. O of n is called linear time, since the runtime is directly proportional to the input size n. O of n log n is just called n log n. This occurs when we have log n iterations or levels of recursion, and in each iteration or recursive call, we perform O of n amount of work. O of n squared is called quadratic time. We see this often when we have two nested loops. O of 2 to the power of n is called exponential time, since the variable n is the exponent in the expression. Finally, O of n factorial, which is n times n minus 1 times n minus 2, etc. until we get to 1, is just called n factorial. Another way to think about this chart is to think about the shape of the graphs that each of these expressions represents. I've graphed all these expressions onto Desmos and linked this graph in the description below, in case you wanted to play around and look at these graphs for yourself. What you'll notice is that as n approaches infinity, the expressions will fall in a certain order that aligns with the complexity chart on the left. So a tip is to think about the graph of the expression as n approaches infinity. This can also help you remember the two rules of dropping constant factors and lower order terms, because those things don't actually affect the shape of the graph as n approaches infinity. Alright, now that we know what Big O analysis is and have some basic rules, let's do some practice problems. Let's say we're given this piece of code. This function takes in an input number n, and then it just immediately returns 1. This has a constant runtime, since the runtime does not depend on the size of the input n. Okay, what if we're given this piece of code? it takes in an input n, and then it prints all the numbers from 0 to n. This piece of code has a linear runtime, since the runtime is directly proportional to n. What about this piece of code? This function takes in a number n and a Boolean bool, which could either be true or false. If bool is true, then we print all the numbers from 0 to n. Otherwise, if bool is false, we immediately return. Well, if bool is true, we have a for loop with a range from 0 to n. So that looks like linear time. If bool is false, that looks like constant time. In Big O analysis, however, we only care about the worst case runtime. So we ignore the constant term and we end up with O of n, or linear time. Alright, let's take this piece of code. We have a for loop that prints numbers up to n, and then a for loop that prints numbers up to 10. Well, the first for loop looks like it's linear time, and the second for loop looks like it's O of 10. But in Big O analysis, we drop constant factors, so we can change the O of 10 to O of 1. And finally, we can drop the O of 1 term, since in Big O analysis, we also drop lower order terms. So this is O of n, or linear time. So far, we've only been talking about time complexity. So let's do a problem with space complexity. In this function, we are building a matrix with r rows and c columns, and we want every element in this matrix to be E. Since the matrix has r rows and c columns, the space complexity is r times c. This problem is meant to demonstrate that the input size isn't always n. Sometimes we have to create our own variables and define the complexity in terms of those. An additional note is space complexity is typically more simple than time complexity. It's not often we see space complexities involving logarithms or factorials. Alright, here's a summary of the things we talked about today. Hopefully it was helpful for you, and thanks for listening.